Alrighty, video 3 here, we're going to look at ethers. We're going to look at epoxides, and then the rest of it will be covered in video 4. We're largely done with alcohols, except we will see in this video how diols can be made from epoxides. Okay? Now, make sure you're good with the alcohol stuff before, okay? Because if you are, particularly these ethers that we're going to briefly look at to start will be much easier. Okay? So let's jump into that. We begin with the reactions of ethers. And as you know from these functional groups, right, a alcohol and an ether aren't too different, right? One's an alkyl group, an oxygen, and a hydrogen. Then we have an alkyl group, an oxygen, and another alkyl group. And if we think about that OH leaving group and that OR leaving group, they're actually pretty similar to one another. They have nearly the same basicity. Right? If we're thinking about pKa's, we got about a 15.7 here and a 15.5 over here. Yep. So on their own, they would still be strong bases. So they'd be a bad leaving group. Okay? So just like in alcohol, an ether has to be activated before it can react, right? We saw all the ways to activate alcohols. Same sort of thing has to go on with an ether. Okay, so we're a little more limited because of that lack of hydrogen over here. Okay, but we can still activate an ether by protonating it, just like we did with an alcohol. Once an ether is protonated, it can undergo a reaction with either HBr or HCl. Okay, we don't react with HCl in this case. I might have misspoke before. The ethers themselves react with HI or HBr. They do not react with HCl. Alcohols can react with HCl and needs a catalyst. Ethers, not going to happen because chloride is too poor of a nucleophile in this case. So look at the overall mechanism here. Very similar to an alcohol. Okay? We use a strong acid, protonate the ether. That gives me a better leaving group. Okay? So then with some heat, either iodide or bromide can come in here, replace the leaving group, right? Turn it into an alkyl iodide or an alkyl bromide. And now you actually have an alcohol as a byproduct. Okay. And this cleavage reaction right here is going to occur via an SN1 or an SN2 reaction, depending on the structure. We'll look at that next. Okay. But what I was alluding to before, right? Because of the lack of proton, like alcohols that have that proton in the end, ethers don't. So because of that, all of those other reactions that we learned to use with alcohols, right? Cyanide chloride, PCl3, tosyl chloride, none of those can be used to activate ethers. Yeah, only for alcohols. So really, it's just this reaction we're going to be thinking about for ethers, activating them by protonation using HI or HCl. Okay. In this situation, if you have a tertiary ether, okay, that would form a tertiary carbocation. So it should logically follow in your head now that, okay, that will work by an SN1 mechanism because of the stability of that carbocation. Okay? If that isn't the case, then it'll be SN2, which we'll have on the next slide. But here, this mechanism should make sense. The acid protonates your oxygen, okay? And it converts your leaving group. This first step is activating the ether, giving you a better leaving group. Okay? Then that leaving group departs to produce the carbocation intermediate. That's the SN1 part. Okay, extra stable. That's why that's able to happen. And then your nucleophile comes in, iodide in this case, and attaches, and your reaction is done. Okay. But again, if this step right here, the departure of the alcohol as the leaving group, okay, if that creates an unstable carbocation, then it's not going to happen. Must be an SN2 reaction. So in that situation, protonate, okay, then the nucleophile comes in and kicks off your leaving group all at once. Okay. Favorable for two reasons here to go by SN2. Reason number one, we just talked about, it's a less stable carbocation, so it's not going to form, but also there's less steric hindrance. It's easier for that nucleophile to come in and attack. Okay. So that's why we have an SN2 reaction in this case. But those are the only reactions of ethers you really have to worry about. If there were an elimination reaction, then the alkene that would be formed would just react with HI or HBr in solution to form your substitution product anyway. So you don't have to worry about elimination reactions of ethers. Okay? That's good. And because ethers are so unreactive, they're typically used as solvents. You'll see some of these used in the labs, right? Diethyl ether, the original antiseptic. THF, tetrahydrofuran, right? Dioxane, another one. Really common to use as solvents for organic reactions because they don't react all that easily. So just one reaction to worry about for your ethers, reacting with HI or HBr. Okay, protonation, leaving group nucleophile comes in. Just know if it's tertiary, it's SN1, the others will be SN2. How about other functional groups? Okay, for the rest of video 3 and then video 4, we'll look at everything else that's listed in the title, starting with epoxides. Epoxides and diols here in video 3, and then amines and sulfur-containing compounds in video 4. This is old. You should recognize this from chapter 6. Okay? An alkene plus a peroxy acid, right? Maybe MCPBA comes to mind, metachloroperoxybenzoic acid. That's the most commonly used one. Alkene plus peroxy acid produces an epoxide and a carboxylic acid, right? The carboxylic acid came from the peroxy acid. It dropped a hydrogen, or excuse me, an oxygen that went to the alkene to form an epoxide. Yep. So that is how an epoxide is made. Old news. Yep. We can also do an intramolecular reaction, yep, if you've got the right kind of conditions, right? Let's say we took an alkene and reacted it with chlorine and water, right? That's going to form a hydrohalon, also from last semester. Right? So you've got an oxygen, an OH, right, on one end, and a halogen on the other. But you could form this with bromine as well. In this situation, if I take this compound and expose it to sodium hydride, and keep in mind that's Na plus and H minus in solution, that H minus is a strong enough base to deprotonate this hydrogen. Okay? That leaves you with an O minus. That is going to come in and attack this carbon right here, kick off chlorine, and you formed an epoxide from an intramolecular reaction. So 2 ways to form an epoxide. This is actually kind of, you can think about this like a modified Williamson ether synthesis, okay? Again, from earlier chapters. Now, even though the leaving group is the same, if we're looking at epoxides, right, we still have an oxygen leaving group. Think about the leaving group as being similar to an ether. Epoxides are more reactive than ethers because of the steric strain that's contained within that 3-membered ring. Okay? Thus, you can actually take epoxides and directly submit them to nucleophilic substitution reactions. Okay? But the conditions are important due to the reactivity. Yeah? But look at those differences in activation energies. Right? One for diethyl ether, which we were just looking at, that kind of ether, and one for ethylene oxide and epoxide. Right? The epoxide has a much smaller activation energy, right? Even though we have the same type of leaving group, all because of the steric strain in that 3-membered ring. You know that 3-membered rings aren't favorable. Okay, so let's think about the conditions themselves, because this is the tricky part of epoxides. Make sure you put a star down in your notes, right? You have to pay attention to the conditions if you have an epoxide. Do you have acidic conditions? Do you have neutral conditions? Do you have basic conditions? Yeah, so let's think about epoxides in an acidic solution. Okay? Well, just like before, we know that oxygen is basic. So if I have an acidic solution, I'm going to pick up a proton to even further activate my epoxide. Okay, so my acid has protonated my oxygen, and then my halide that was kicked off here comes in, backside attack, boom, boom. Right? I have formed my final compound. Okay? What's the difference here? Well, it looks pretty similar to what we've seen before, but notice there's no heat in here. Right? It says that down at the bottom as well. It occurs at room temperature. You don't have to heat the solution. Epoxides can actually just react at room temperature, which is beneficial. Epoxides are more reactive than alcohols and ethers. So much so that you can even use poorer nucleophiles to come in and attack and open up that ring. It doesn't have to be as strong as bromide. Looking at what we've got here, right? again, acid-catalyzed mechanism. First step is always to activate your epoxide, and then we can even use methanol, right? A much weaker nucleophile to come in here and attack. Then at the end of the day, I've got a protonated ether in that case. My base is going to come in and take that away. Right? HB plus here is just any sort of general acid, anything that can protonate that epoxide, and then B is your base, conjugate base from up here. But then the question comes up, what if the epoxide's not symmetrical? Right? Because this epoxide is. It doesn't matter where I showed the nucleophile coming, here or over here. I would have gotten the same product in 3D. If your epoxide is not symmetrical, then you've got one more factor to pay attention to. And this is, again, why the conditions are important. Okay. First step, the same. Protonate your oxygen. Okay. Now, if you have acidic conditions, the nucleophile attacks the more substituted ring carbon. Okay. So in this case, I compare my two carbons. Okay. This one has two hydrogens. This one has a hydrogen and an alkyl group. This ring carbon is more substituted. This is the one that gets attacked by the nucleophile under acidic conditions. That's the key, underline that, right? Acidic conditions. And we can see why if we look at the transition state when the bonds are breaking. Okay? Looking at the attack of the more substituted ring carbon, right, after the epoxide has been protonated, we see where the delta positive is, right? Delta positive here and delta positive right there. Okay? And after the epoxide's been protonated, it's actually so reactive that that carbon-oxygen bond, as you can see here and here, starts to break even before the nucleophile bond starts to form. It's almost like it gets scared as this begins to approach and panics and breaks. So when that bond starts to break, it puts a partial positive on the carbon that's losing the electrons here. And you want that to be on the more substituted carbon, right? Because of stability due to hyperconjugation, back bonding. Right? And that actually gives this a special name if you see it in your book, because of this bond this bond breaking before the nucleophile bond actually starts to form. It's considered a hybrid SN1, SN2 reaction. It's kind of a mixture of the two in one. It's an SN1, SN2 hybrid. It's called that way because the leaving group leaves early like it would in an SN1 reaction, but you don't fully form a carbocation like you would in an SN1 reaction. So it's a little bit of SN1, a little bit of SN2. But again, just know that you attack the more substituted ring carbon if it's acidic, and if you show it as an SN2 reaction, that's fine. Yep. But if the conditions are different, if you have neutral conditions or basic conditions, then the reaction changes, and it still occurs, right? Even though here we're showing the epoxide being protonated, we can still react an epoxide under a neutral or basic conditions because of the ring strain. Okay, so if that's what you have, right, neutral or basic conditions, then the product is switched. Okay, we've got a change in reactivity. Now your nucleophile comes in and attacks the less substituted ring carbon, okay, because of sterics. Right? With the alkyl group here, it's kind of getting in the way of the nucleophile. So this nucleophile is going to come in and attack whatever's easier to get to. Yep. And in that situation, it's a less substituted carbon, purely a steric argument. Yep. And we typically use stronger nucleophiles under these conditions. Okay. So acidic, your nucleophile attacks the more substituted ring carbon. Neutral or basic, your nucleophile attacks the less substituted ring carbon. And then to get to an alcohol, your final product, right, you have, of course, have to protonate that in a later step. Couldn't do that all in one pot because then it would just protonate methanol. So it's a two-step reaction. And these epoxides have some roles in synthesis. Okay, because it's so reactive, these epoxides, they're actually a really nice starting material because they're going to react with a variety of nucleophiles. As you see here, I can take an epoxide and react it here with a deprotonated terminal alkyne or with an amine, okay? Form a new CC bond there, right? I can easily add things onto my carbon chain because of the reactivity of that epoxide. So that's why we see these epoxides so common. Even though they've got that ring strain, you might think, okay, they don't like that, they're not super common. You will see them pop up pretty frequently. So let's quickly revisit last semester, preparing alcohols from alkenes. Now, in this situation, right, when we had an alkene, we added an acid, right, that formed a carbocation, right? We're following Markovnikov's rule here, putting my carbocation on this carbon, right? Because my hydrogen goes to whatever carbon has more hydrogens, gives me a secondary carbocation. Then I hydride shift over to form a tertiary carbocation. And then when I add in water, it comes in here, right? Lone pair on oxygen comes in, attacks. I have a protonated alcohol. I deprotonate and I get an alcohol as my final product. It should be an H+ over here as well. If you have the acid-catalyzed addition of water, like we have here from chapter 6, you have to worry about that carbocation rearrangement. Okay? So here is another synthetic advantage. If you want to avoid that carbocation rearrangement, you can first take your alkene and convert it to an epoxide. Right? Same product, or sorry, same reactant here and here, but look at this. Peroxy acid to take it to an epoxide, then deprotonate with sodium hydride, then you add in an acid to get your final alcohol product. Now you've put the alcohol where you want it here, on C2, instead of putting it on C3 like we did before. And then that's an easy mechanism here. When you've got hydride, right, it's under basic conditions, so it's attacking the less substituted carbon, SN2 reaction, boom, boom, which I didn't mention before actually, neutral or basic conditions, it's no longer the hybrid mechanism, it's just SN2. So here we've got hydride coming in, easy reaction, no carbocation rearrangement to worry about. So if you see it on your homework, you can use any hydride donor. Lithium aluminum hydride is a really common one, LiAlH4, or you might just see it abbreviated as LAH, lithium aluminum hydride. One final possibility, right, if we have basic conditions, is the formation of a diol. We will see shortly where these diols are advantageous. If you have an epoxide here, right, plus now we've introduced it to hydroxide, that's a good nucleophile, so it's going to come in and attack your epoxide. Okay? Then if you you protonate your final product, you get two alcohols next to one another, trans 1,2 diols, okay? Also known as glycol or vicinal diol. They form trans specifically due to backside attack in this situation. So these two are going to form trans to one another always, and we get two products from that anti-addition. You can form cis diols if you want to. Know these reaction conditions right there. Alkene, osmium tetroxide, and then peroxide and water, two-step reaction. That gives you a cis diol. A two-step reaction because it does a syn addition. And here's what that mechanism looks like, right? It's a cycle addition. So here you go from your alkene, attacks one of your oxygens, kicks pi bonds over to osmium, more pi electrons come over, you form that, it's called a cyclic osmate as your intermediate, and then peroxide and water kick that off and you get your cis diol. Okay. I'm not going to test you on this mechanism. I will, jumping back a slide here, I ask you to know that reaction, those conditions, if you want to make a cis diol. Going back a slide again, if you want to do trans, piece of cake, just and epoxide and hydroxide together. But if you want to do cis specifically, know those conditions. Okay. So that wraps up what we've got for this little intro to diols. Okay, it's kind of a random addition there at the end. We will see in just a couple of chapters the role of diols as protecting groups. one more video to go. Chapter 4, we'll look at the remainder of the groups. But the big takeaways here, that quick introduction to ethers, and then all these reactions of epoxides. That is the more significant thing from this video. Know what epoxides do, what carbon's getting attacked, identify the conditions, and be able to correctly predict your product.